Coriolis, to say a couple of words about yourself, about LIP6, basically, what you guys are up to, a tiny bit snippet from the history, what have you been doing, what are your plans, and then maybe present Coriolis. Would that work for you?
Okay, very good. I
Yeah,
was
thank you.
intending to talk about that directly inside the presentation, but that's very good for to take some time just before to set up the context. So, should I begin, or we are waiting?
Please go ahead. The floor is yours.
Okay, thank you. Welcome everybody. I'm happy to meet you today. So I will before I start the presentation, as Mirjana requested, I will talk a little about myself and the laboratory I work in. So I work at Sorbonne University in the LIP6 laboratory, which stands for Laboratoire d'Informatique de Paris 6, which is the former name of our university. So now it's just LIP6. And I'm working in a team inside the LIP6, which is the CIAN team for, in fact, an analog mixed design. In the LIP6, we have worked for more than 30 years on digital design and analog design. I myself worked on about 30 years. I worked on this project from the start, for almost the start. So we gather a lot of experience, and we have a unique experience in LIP6 because our team is working hand in hand with digital designer who make circuits and also analog designer. So we have a unique connection between them, and we can very easily share information and exchange requests between them. So we can know what they want, what their problems are. So it's easier for us to develop software that match their requirements. So in that spirit, we have first developed the Alliance toolchain, which is purely digital and which was developed in the 90s, and which works on symbolic layout, which is a kind of a different layout than the GDS that you can have usually. It's the idea is to work on a layout which is not the real one, but which is scalable, in fact. You use a slightly degraded design rule, and then you can scale by a simple homothétie your layout to match the target node. So, of course, you have a slight loss of performances, but still, the point is that you can cross technological node without to have to redevelop your whole design. This approach was good in the 90s with very lower nodes, lower technological nodes. It's worked until around 350 nanometers. Below that, it started to have problem because the shrinking rate of the different layers in a design was not the same. Typically, the metal layers shrinks faster than the, for example, the diffusion layer and the gate layer. So it was starting to having problem, but still it's a good basis to work on, Alliance. And from that, we developed Coriolis, starting in the year 2000, and we completely rewrite the toolchain to support directly the target technological node. It's real layer, GDS equivalent. So, and parallel to that, we also introduced inside Coriolis analog components, I mean analog support. We started to develop the digital part, but then we extended toward analog design of course, with a very close dialogue with the analog designer. And this is how Coriolis was made for the analog part. So in my presentation, I will focus, of course, on the analog part, but you should not forget that Coriolis is also a full-fledged digital place and route system. Another point is that Coriolis focus mainly on the physical design, not the synthesis part. And that is true for both parts, which is the digital part and the analog part. That is, we take specification and then we make the physical placement, but we don't compute or we don't manage the logical part. That is logical synthesis mainly for digital part and analog sizing for analog part. So I think that's okay. So I work in a very small team for now. I think we are 3 to 4 people, depending on how you consider the things. But still, we have made something, and mainly last year, yes, we did send to the foundry a chip in TSMC 180 nanometers, which is called the LibreSoC, which is part of another project that we are collaborating with, and which it contains, of course, a huge part of digital design, but also a small part which is a PLL, which is an analog circuit, and which, as far as I know, has worked. That is, we successfully checked that the PLL was working. We did not completely check the design for now because we have a problem with the pins. We have a problem with the packaging, and we need to implement a PCB to really use to put the chip on it, and we don't have done that yet. So that prevented us to still to check that it was working, fully working at least. But still, the analog part was working, and it was done with Coriolis. So now, maybe I will start the presentation itself, if you have no question. Was it sufficient? Okay.
Thanks, Jean-Paul. It was. Please continue. Yeah.
Thanks. So now I will try to find open share tray. I will share my desktop. So I hope you see the presentation now. So
yes,
I assume.
Please.
Okay, thank you. So I will start. So this is the plan. First, a little introduction that I just mostly done. Then I will make a small introduction about the digital place and route, because it's mandatory to understand how the analog parts work. Then I will, of course, switch to the analog place and route, make a little point about the state of the tool chain as of now, and finally show you some, I hope, nice demonstration of what we can do with Coriolis. So, as I said, I am working at the LIPSIS laboratory of Sorbonne University, which is part of the CIAN team. We have more than 30 years of experience in this field of research. One interesting point about analog designer is that they don't trust automated tools. At least until now, there is no automated design tool for analog designer which is accepted. You can find academic publication about tool chain or methodology to perform analog designs, but in the industry at large, and to my knowledge, people analog designers are mostly doing things by hand. And they are constantly redeveloping everything. And this is because they are not happy with the way the automated tools work. And our conclusion at Sorbonne University is that if you want a tool to be adopted by the analog designer, in fact, you have to let the analog designer make the choice he wants. So we didn't focus on a fully automated toolchain, but a semi-automated toolchain. That is, every tedious work is automated, but still it's the analog designer, we make the important choices, and we let them make those choices. So we don't get away the freedom of doing what he wants. This is, I think it's a very important point for toolchain to be accepted in the industry. So now let's have a look at the digital place and route. How does that work? In the digital world, you have standard cells, which are here on the left side. So your design is made of hundreds of thousands of little gates, which are atomic elements containing transistor. I mean, for example, this NAND, NOR, XOR, so atomic digital element, plus, usually the biggest one, flip-flops, that is memorizing element. You have also a dedicated block, but it's we won't talk about it here, like SRAM and the big memory blocks. So the world, what we want to do is to place all those little cells, call it standard cells, inside a usually rectangular area, divided in slices, and without overlap. It goes without saying that you cannot place two cells at the same in the same space, because the design won't work. So the first step is just to place like that. So usually there is much less white space, of course, just for the design. There is usually between 2% and 5% of free space. So this is the first step, to place inside a dedicated area all your cells. And then we perform the routing. The routing is the task to draw the electrical wires between all your little cells. So what you have here in bold drawing, in fact, is the G-cell grid, because the problem is too big. You cannot handle the routing of the wire in a flat fashion. I mean, if you want to draw all the wire, exactly the real wire, directly, the problem is just not manageable. It's too much data, and the processing power that we have now, it's just, it cannot suffice. So what we do, as often in those cases, we reduce the size of the problem. And we cut the place and route into two stages. The routing into two stages, which is the global routing, followed by the detailed routing, and the hinge that hinges around the G-cell structure. What we do is that we divide the whole area into squares. For example, here, the square is 10 track by 10 track. And we resume that area to just one point. We said, and we build a coarsened routing grid into which each point is one G-cell. So you can obviously see that if you have 10 track by 10 track, you reduce the size of the information that you have to manage by 100. So with this kind of reduction, we can handle the routing, the global routing, straight. So we perform first a global routing, which will give us the path of each wire, but on a coarsened grid, and then we perform the detailed routing. The detailed routing takes the results of the global routing and then select onto which track we are going to place exactly the wires. And with these two steps, we can perform the routing. So, and the point is that we have G cells. So the element to remember is that we built upon G cells that describe how we partition the space. And just a little detour, the metal layer are given specific orientation. We don't route in any direction, any metal in any direction. For example, the metal 1 here is vertical. Then you have the metal 2, which is horizontal only. And finally, the metal 3, which is vertical. This is called the Manhattan routing, because it's like the city of Manhattan with a wire straight, either vertical or horizontal. No diagonal wires, only horizontal or vertical. It's classic. So now that I have presented the digital part, we are going to enter the analog realm. And first, I will present the overall design flow for an analog design. So first, you have to perform the analog design itself. I mean, choosing what analog function you want to implement. A PLL, a DAC, digital to analog converter, or the opposite, or any kind of circuits. So first, you design your circuit in terms of transistor. An analog design is transistor, capacitor, and resistor. But just that without shape, I would say. You just have the size of the component you want to put on the silicon. The second step is the sizing. Once you have the structure of your circuit, the netlist, you may say, you have to size your component so the requirement of the design are met. Meaning for a PLL, for example, you want to target a certain frequency, a certain working frequency. So you have to size your resistor, capacitors, and other components so that your PLL is really working at that frequency. So this is the sizing. Then, in our case, we translate that netlist into a Python one. So it's just an equivalent. We have a netlist of components of transistors. And here is where Coriolis enter the play. It performs the analog place and route and generate a GDS file, which could be the layout of your analog design. But usually it won't work straight because you have parasitic components. When you perform the sizing originally, you just said, okay, I want to work at that frequency, and you cannot account for example, the wires or all the parasitic capacitance or the parasitic resistors that will appear due to the wiring or the cross-coupling or many effects that appears when you perform a layout. So what we do after obtaining our first version of the layout is a parasitic extraction or any kind of measurement to see that the parasitic added by the place and route didn't perturbate too much the functionality, the feature you want to reach. And what you usually do, they perform some change. So what we do is that we check if the feature the requirements are met, and if not, we start again the sizing, but this time with the knowledge of the parasitics. Here we extract the parasitics, and so we know what kind of parasitic we will have, and we resize the design using those parasitics. The point is that even if there are parasitics, the design will not change too much. So it will be a slight adjustment. If it is big adjustment, it just means that your whole design is not correct. So, and we loop again until we converge. So we perform sizing again, analog place and route again, parasitic extraction again, and we see if we are reaching or if the requirements are met. And usually after 2 or 3 turns, it does, and we are finished. So the point is to have something which is quite adaptable here, or versatile. Now I will introduce the analog design, the analog devices. The devices are the atomic elements in an analog design. The devices here is a transistor, but it can be a resistor or a capacitor. So here I showed only a resistor, and the interesting point is that contrary to digital design, analog components can be very big and are usually very big. For example, here the transistor can be very high. There is always some kind of misunderstanding because we want to say that it's the high, but in fact it's here for an analog designer. The width of the channel, it's the length of the channel. Okay, I'm confused. Okay, so forget exactly what I said. We have a height and we have a width, and this height will be enormous, and we don't have the space, or it will be a terrible waste of space if we just put that transistor like that. So what we do is that we fold it. Instead of having one big transistor, very long transistor, we have two transistors of half the length. And we can continue by splitting in four the transistor. So what we got is a curve with the number of fingers. Here we have the transistor, and each gate is called a finger. Here we have 2 fingers, and here we have 4 fingers. So we got a curve here with the number of fingers, 1, 2, and 4, and this curve is convex. It's quite easy to guess from the way we do it. But of course, each time we split the transistor, we introduce parasitics. This is part of the problem that when you make your computation, you have one transistor, very nice, but obviously when you have your design, you will have this one, which is not completely equivalent to this one. You have parasitics. So we have our convex function, and this has a nice implication about the way we do things afterward. So now we will see how we perform the device assembly. This is the placement for an analog circuit. And this is the way we do it in Coriolis. You have many ways to do that thing, but in Coriolis, we choose to do it in a slicing tree. I hope it's. I made the white bars, the white lines, to delineate the slicing tree. A slicing tree is a very simple structure which occurs often in CAD EDA tools. It's just a recursive partition of the space. Here, the first level of the slicing tree is horizontal. We have vertical lines here. We have 3 vertical lines, this one, and this one, which separate our horizontal space into 4 partitions. This is the first level of the slicing tree, which made 4 horizontal partitions. Then each one of the horizontal partition is vertically partitioned. Here, the leftmost partition, you have one part here, the second part here, and the third part here. So 3 parts for the first horizontal partition. Then here for the second horizontal partition, we have only 2 parts here. We have 3 parts again here, and we have the last, the rightmost part is just one device. So we stop here. And then we go again. This vertical partition is then horizontally partitioned, each one. This one is partitioned horizontally, this one is not partitioned, and this one is partitioned in 3. So it's just a tree. A slicing tree is a recursive structure where you perform recursively and alternatively horizontal then vertical partitioning. and I did name the devices D1, D2, D3, D4. So each green rectangle is an electrical device. It could be a transistor, a resistor, a capacitor, whatever. So the second point, there is a feature which is almost mandatory in every description of an analog design is the symmetry. For a lot of reasons, and mainly reducing parasitics or to have a very accurate design, sorry, you have to pair the design. You said, for example, here that D1 is symmetrical to D11. The device will be exactly the same. Same goes for D2 and D10, for D3 and D12, D8 and D9. Of course, there is a mandatory condition, is that the slicing tree itself is symmetrical. You cannot tell that D1 is symmetrical to D7. This is completely impossible. So you can describe symmetry only between transistors that are symmetrical inside the slicing tree itself. But you have a mix of symmetrical device, symmetrically paired device, and non-symmetrical device, like for example, D5, D4, D5, and D6. So we have two kinds of device, the just standard device and the paired device, symmetrically paired device. So finally, what we do inside Coriolis, always, after having our slicing tree and our symmetrical constraint, we build the G cells. Remember, the G cells are the structure that we use for the global routing in the digital world. But in Coriolis, we have extended this mechanism to describe the slicing tree and the partition, the area partition of an analog design. So we have four kinds of G cell. In that case, we specialize the G cells. We have G cell for the devices, the normal devices. We have G cell for the symmetrical devices in red. So they are both devices G cells. And then we have routing G cells, channel G cells. Here, for example, we have a vertical channel, and here we have a horizontal channel, and both are G cells. They are some kind of specific G cell for specific purpose, but they are G cell nevertheless. And finally, we got struts. Here, struts are added to describe the space that is left blank. Sometimes, when you perform the sizing of your walled circuit, you got extra space. And this is the struts are here to describe that extra space. It has also some constraint about the way we can put wire inside them. Okay, so why are those called channel? It's because this is where the connection will go. An important thing to know for analog design is that due to the problem of parasitics, you don't want the connecting wire to go over the devices. The wire must always go in a separate area. They must contour the devices. No wire over the devices. This is why this is called channel, because this channel will contain the wires. So finally here, I did put the G cell that we have. This is not a tree. This is completely flat structure, but we can still see where it comes from, where the slicing tree was. But you get a flat structure of G cells. And one important point is that it's the same G cell as for the digital routing. With the G cells, we now can perform the global, then detailed routing. So here I presented a wire in blue connecting D1 and D11. D1 and D11. And as I said before, the wire, except for when they reach devices, they connect to their devices, goes only inside channels. So here the horizontal channel, then the vertical channel, then horizontal channel, vertical, horizontal. So we go only in channels. Another point I did represent here is that, like the devices, for example, I said that D1 and D11 were symmetrical. We can also put constraints on the wires, in this case, this wire, and said that the routing must be symmetrical. Symmetrical regarding this axis is here, we have an axis of symmetry. And we said that that wire must be symmetrical regarding this axis. And the router is doing his work. So this is the first case of symmetry. Then we have a second case of symmetry when we have two signals here connecting D3 and D8 and D9 and D11, D12, sorry. So these two wires must be routed symmetrically. Typically because you want exactly the same parasitics on the wire. On this wire and this wire, you want exactly the same parasitics. Because often in analog design, it is not the absolute value which is important, it's the differential value. You can tolerate that a value can change or inside an interval, but what you don't want is that two identical values must stay identical. So this is why we have symmetric routing, either for one net or for two nets. Now, I will start to present how Coriolis works inside. How does it manage all those layout generators? What is the software structure? It's a bit more technical and it's specific to Coriolis, but if you want to dive into it and just look into things and change things to make checks or experiments, this is an overall view of how it is made, or how is it organized. So basically, if I take a transistor, we got a C++ interface, which is fixed. Of course, a transistor has only four nets: the gate, the bulk, the drain, and the source, and electrical parameters like wire width and length. Of course, there are other electrical parameters, but for the sake of simplicity, I did just put the two basic ones here. This is the logical view. But in front of the logical view, you have to create your layout. So to do that, we have layout generators, which are written in Python. So the transistor is calling, when you want a layout, you call the Python generator, and the Python generator is able to generate any shapes that you request, within reasonable limits, of course. So it can generate the folding, the transistor with one finger, with two fingers, or with four fingers. And it can return the layout or only the sizing of the devices. Because in the preliminary stage, when we only want to evaluate the global placement, the placement of the analog design, we may not need the complete layout. We just want the bounding boxes of the layout. So this is what we can get here. So this is the general structure. Okay, what generator do we have? What transistor generator do we have? We have a lot of paired devices, because in analog design, a transistor is usually not alone. It's usually, they come into pair. And instead of letting the user create by hand its own pair, we just directly implemented the most used pair that are available, the differential pair, the common drain, cascade, common gate, and so on. So all these are very common pairing transistor. And this is important because inside Coriolis, we implement them as just one stack. I will present just in a few slides what is the stack, but basically you must understand that those two transistors, while they are in the schematic, they are separated. In the layout, they are closely intertwined. In fact, they have one bit of of this one, then one bit of this one. Their fingers are completely intertwined. We will see that in just a moment. So here is a more detailed view about the design, how Coriolis is organized, and where you can find things. Again, this is for people who wants to put their hands inside. So the basic structure here is in the Hurricane database. This is part of Hurricane. So we provide all the transistors. Then the Python generator are in the Orochi tools. We are working with Japanese people, so I choose some name of Japanese wines. So the layout generators are all located in Orochi. So transistor, resistor, capacitors. Then the assembly of the devices, that is the implementation of the slicing tree, is done inside the Bora tool. Bora is also a wine, the name of wine. So we have the slicing tree, which is a C++ structure, but which can be configured, controlled through a Python interface. We export all the C++ structure to the Python level, so we can use scripts afterwards. So upon that, we built analog design, which is inside the tool Karakaze. And analog design is just some kind of middleware that or kind of helper that simplify the manipulation of both the layout generator and the slicing trees. So with the analog design, which is a Python class analog design, you can describe your analog design much more easily. But this is the example of if you want to change, if analog design doesn't suit you, if you don't like the choice I made to describe an analog design, you can change it. You don't like it, okay, you rewrite analog design to something else, and you can have your own interface to the rest. And finally, the last level is the user design, which is make use of analog design. And that this is what you write. And I will show you in the demo some example of the scripts that you can write that describe your design. So next, I will make a little detour by the device generator themselves, because they are, it's also interesting. So here I did represent three different designs. We have the single transistor, we have the dual pair transistor, and the common source pair. This is just to show that we can have different kind of transistor, and in fact, they all rely on the stack. The only work of the transistor DP and CSP level is just to send the right parameters to the stack. And the stack is the script which is tasked to build the set of fingers for the transistor, the device itself. The idea is that as I am coming from a software background, there is something I take as a personal insult, is that to have to rewrite the same code or almost the same code twice. And what is shown is that if you write the transistor code, then a dual pair code, then a CSP code, you see that it's almost the same. So I did just group all the code inside the stack and just set a set of parameters. So here is an example of how the stack generator works. Basically, what we call a stack is just a series of transistors. You have Here we have 4 fingers, and the device you are really implementing will only depend on how you connect the drain, gate, and sources to the various tracks here. So the idea here is that the stack generator, when you call a stack generator, you just pass it a kind of a string describing how you want to connect the source, drain, and gate. Here it's just a simple transistor, so all the drain are connected to the B1 track. B stands for bottom 1 track, bottom 0 track. The number of tracks is increasing from the device itself, from the transistor itself. So bottom 0, bottom 1. And here is for top 0. And you can say the first drain here, it's a drain, not a source, but because you can reverse source and drain sometimes, if you want. So here we have drain first. And we say that the first diffusion area is a drain, and it's connected to the B1 track. So in fact, B1 will be effectively the drain. We have drain, we have gate, and we have source. B0 will be the source, B0 will be the gate, and T0 will be the source. And so here it goes, we have DB1, G connect to B0, so the first gate connect to B0, then the first drain connect to T0. And we go on. And we can describe completely the stack. There are other parameters, of course. For example, we can also choose the width of the wires here on the track. But I didn't put it in my schematic to not be too overloaded, too overcrowded. And you can see that if you have multiple drain, you will have D1 or G1, S1, and so on. And you can build any kind of transistor. You can construct all the pair of transistors that I did show earlier with this schematic. So it goes very easily. Once you have the stack generator, you have all the devices you want. Here is an example of layout. So what we see here that I didn't show in the previous schematic is that you have a guard ring here. The guard ring is optional. I did draw it for the sake of, because it's nicer. So you have the guard ring, and you see that we have the guard ring which is connected to here. It's the drain. So it's a source drain. No, it's a drain bulk connected. Then the leftmost and rightmost transistor are dummies. And you can see it because their gates are connected to the guard ring, which is the ground, in fact. It should be the ground. So here we are connected. Then we have the transistor which is starting. And you see here a little bit the track. This is the first track, the second track, and you have one track here at the bottom. The track is using all the gates. So you see there is only one gate. All the gates are connected to the same track. But the drain, or the source, I don't know, I don't remember, are connected to two different tracks. So I don't remember which kind of dual pair of transistor is it, but you can guess it by the connections, and you can find it. So this is an example of layout. Now, I will dive into one feature which is essential to Coriolis and which is very, very interesting, is that in Coriolis, we truly do mixed design. By saying that, I mean that usually when you develop an analog design, you will have either analog on top approach or digital on top. Analog on top means that you consider your whole design as an analog design into which you put some black boxes that will contain the digital part. Conversely, if you perform digital on top, you assume that your design is fully digital and you put one or more black boxes containing analog design, analog components. But the problem is that in either approaches, the digital part is not really aware of the analog one, and conversely. So it's not well integrated, and it works, of course. Tons of design are made, but it's not elegant, and it's not. It causes problem because you have to make some go back and go forth between the two realms, and you have to adjust them carefully, and it can take time. So instead of that, in Coriolis, what we have is two kinds of placement. Here, the regular area, you see here, is the digital placement, that the digital placement area that we have seen earlier. And inside that area, there is a part which is dedicated to an analog design. But it's the same structure, I mean, G cells, but our G cells are not restricted to square, but can take any form. So any rectangular form, of course. So what we have here is one G cell structure. We came to that structure we have two different placements because, of course, digital placement, it's obvious, does not work like analog placement. As you have seen, analog placement is a slicing tree, while digital placement is a completely different matter. But once we have performed the two placements, the resulting data structure is unified. We have one G cell area, and then on that G cell area, we can perform the global routing and the detailed routing on the wall. There is no difference between the analog routing and the digital routing in either the two steps, global or detailed. This is the strength of Coriolis, its ability to fuse those two aspects. And of course, the global and detailed route have been enriched to support the analog constraints, mainly symmetries. So this is what we have. So now just a little, not everything is working in Coriolis. Unfortunately, this is a very huge program, and we have not very much working capabilities. So the transistor support is fully working. We have capacitor and resistor scripts, but they are not very well written, and I won't consider them as usable for standard users. And now I will show you what we can do really with a GM Shamla. A GM is a kind of amplifier. It's the first stage of differential amplifier. It's the first stage of a differential amplifier. So I will switch to the demonstration. So what we have here, I hope the font is not too teeny. We have this script, gm.py, which is the script which describes the design. So I will run CGT. Okay, and I will run the script. GM, stupid me. Okay, here we are. So what we have here is the slicing tree, the analog circuit with the slicing tree build-up and devices setup. The global routing has been performed, but not the detailed one. The interesting point is that we can show here slicing tree curve. We can only work on one slicing tree at a time. This is where the analog designer works. He chooses the slicing tree, but once he has chosen the slicing tree, he can select the best aspect ratio he wants for the slicing tree. For example, here, we have a table of all the possible shapes for the slicing tree, with all the possible shapes for the devices. Because as the devices can deform, change their aspect ratio, obviously, the whole design can change its aspect ratio. So for example, here, the green line here is the Pareto frontier, that is the optimal solution for one criterion. So here, we can see that it's a very bad one. It's very height and a lot of free space. On the opposite, we can have this one, which is very, very bad. It's the worst of the whole series because very high and very wide. And this one is the opposite. It's the better one, which is the smaller one. So here you can choose but the row size may not be the only criterion for an analog designer. He may have other criterion. This is why we give him the choice. He can choose what he wants to do. So next, I will show what I talked about earlier, the G cells, because the slicing tree cannot be visualized. Nevertheless, the G cell can be. So if I print the G cells, I will remove everything and just display the G cells. Here you can see the slicing tree appear. So you see here a routing channel, the vertical routing channel, the second vertical routing channel, and here we have horizontal routing channel. So you can guess the slicing tree here by just looking. This is just the number, the identifier of the component. So I will redisplay everything. Maybe not the text ruler. Don't want too many things to be displayed. And the global routing has been done, so now we can finish with a detailed routing. So step by step, detailed route. So here, the wire have been detailed routed. And you see here, maybe I will remove the grid. It will be clearer. Okay. Those little dots is because the routing is not finished. I mean, the data structure is still active. And until it's active, it stays little points here. So, okay. Now we can see the symmetrics. I will open the design itself. So it's SRC Alliance. Check toolkit, bench, analog, GM, GM. So here is the script. So what we have, for example, we have VB5. We will look at VB5. We can display the netlist. Oops, here. And take a look at VB5. Here. So here, VB5 is a net with a symmetrical constraint with itself. That is, with the vertical axis of the design. And it's, I don't know if it's clever, but it's really visible, but you can see that it's symmetrical. It has been symmetrically routed. Same goes for VB7. It's even more obvious for this one, which is just a straight line. So VB7. Now we can also see paired routing. So we have AMPP 73 and AMPN 72. So AMPP, where is it? 73. Oops, okay, this one. So IMPP and IMPN 72. Donc I will perform a cumulative selection. to see both net. Where is the 72? Here. So now, here, we can see two nets that have been routed in a symmetrical fashion. Okay, so this is an interesting example. We can also, there is one thing which is interesting. This is an editor. This is not an editor, this is just a visualizer, but still, we can, for example, go into one device. Okay, if you want to see one device, and if you want to see how it's organized, we can select the nets. So we can see, okay, here is drain 1, drain 2, gate, and source. I think it's the one I did show in the previous transparency. And you can go back to the wall design. Here. I have maybe a second example. I can show it quickly because it's funny. So, GM Shamla prog. This one is funny because it's mixed digital and analog. So, and it's a GMD code. GM decode. So here it is. So what you see here is that in the center you have a digital block. This is a digital block. And if we again see the G cells, I will remove everything first, then show the G cells. You see that here you have a perfectly regular area. This is the digital part, which will be routed according to the digital rules. But everything else will be routed in the analog realm, with analog realm constraints. So let's see, everything shows again. No G cell, no edge, and no grid. And then we can perform the routing. Here we are. And we see that everything has been routed. It's not the most elegant. We can choose a more elegant one, because you see here the wires are a bit messed up. We can do better with slicing tree curve. I think this one may be better with a little more space. Ah no, I should have rehearsed a little bit more. Maybe this one. I don't remember which one is good. PNR. No. Okay, maybe it's not important. Bon, I lose it. Maybe first this one. It's a very bad placement, but still. Okay, you see this one. All the wires are very regular. So you can, it's very nice to see. And those little bumps here are artifacts that stay only because the global routing, the detailed routing is still active. To make them disappear, it's quite easy. It's just finalize routing and then they are gone. They are only metal 2 remaining. Okay. So I think this will be all for my presentation. And Of course, Coriolis is completely free software, so you can use it, you can compile it and use it. These examples are free, but they are not meaningful in the sense of electrical design, because they are just here to test the place and route capabilities of Coriolis. The design rule I did use are depends on MOSIS 180 nanometer. I think it's SCN 6M, which is a 180 nanometer technology, kind of fake one. And the sizing of the transistor has been made using a 350 nanometer technology. So from an electrical standpoint, it's complete nonsense. The size of the transistor are complete nonsense. Nevertheless, they are just to be changed. So maybe just one last thing, a little look about the circuit design, the circuit description. As I said here for the GM Shamla, it's a Python script. You define a class which derives for analog design. Then the first step is to define all the devices you need. So here you said it's a transistor. The kind of layout you want to use. WIP stands for work in progress because I'm still developing them. The kind of transistor, it's NMOS, PMOS, or whatever, and the width, the total width of the transistor, the total width, the total length, and other parameters that I let the analog people to comment. So second, you have to define which nets are externals. That is the interface of the design. In fact, it's just a very simplified netlist description. Then you describe the netlist itself. So here again, very simple netlist description. You have the net, and what it connects. Here it just connects one thing, it's not very interesting, but for example, Vout plus connect the D net of the M2N transistor and the D2 net of M9AP and so on. So it's quite straightforward. And finally, most interesting is the description of the slicing tree. This is what goes here. So you start by begin slicing tree, and I used a stacked approach. I mean, you start the slicing tree and then you put things in stacks. That is, you start to push a node. The slicing tree is horizontal by default. The first layer is horizontal. So here we will start with the first horizontal part. We define all the symmetry that we want to do between the nets. So we said that those nets are symmetrical. And then here I push a H node and I push the device. When I have finished the node, I push. Okay, there are multiple levels. So you describe your design by pushing and popping nodes. It's a bit. I should have made a more comprehensive description, but it's quite straightforward. But here again, this is my vision of an interface, as it is done in a Python script, which is analog design, not a script but a class. If you don't like it, you just rewrite it and remade the interface between Python and the slicing tree data structure. It's up to you if you don't like it. And with that, I will finally finish. I will stop sharing. Okay.
Great. Thanks, Jean-Paul. So let us see if there are some questions for you from the audience. Okay. Please. Anybody? Or everything is clear?
It's a lot to process, I think.
Yeah, I believe so too. So, Jean-Paul, would it be possible? I mean, we were recording this video. Would it be possible that we also, when we first time kind of exchange a couple of emails, you sent some information about the Coriolis and documentation. Would it be possible that I share that with the participants
Yes, of
in the
course.
chat? Okay,
Yes.
excellent.
I can also send the slides if you want.
Yeah, that would be perfect because we're pushing all the presentations to MOSAIC, like a GitLab. There is like one project, just bootcamp framework, and then presentations are there so that people can actually, maybe refer to the presentations or go through them. Sometimes it's faster than the video. Yeah. Okay,
Okay.
great. There is something in the chat.
Ah,
Okay, Jorge. Yeah. Yeah, indeed a lot of the digest. So I have a yeah. Jorge from Chile said, great presentation. Thanks so much. Indeed, a lot to digest. Yes. Jean-Paul, this like whole like opus, I don't know even how to say it in English. It's like a really a lot things that you have done. So can you like tell us basically how long did it take you to develop this kind of tool? I mean, it's one person, let's say, like most of the show. So,
um, uh, it depends. Do you want the whole of Coriolis, digital plus analog, or just the analog part?
you can tell us, in the pieces,
Ah,
so that people can actually understand how much one person can actually do full time or part time or whatever.
um, I have worked not exactly full time, but I would say two-thirds of my time for most of 20 years. And but I have got some help. In fact, what I usually do is we have interns or maybe PhDs. More often, you have PhD who develop a first version of a tool. For example, for the global router, we did have a PhD. Which made a great work at developing the global router. But then I did have to rewrite almost everything. I mean, I did take his PhD, his documentation, and I restart completely from the documentation because the ideas were good, but as a PhD is only 3 years long in France, he didn't have time to develop it the way I wanted it because I wanted a tight integration. The maybe more than the time that I made to develop that thing, one important point is that is the integration of the tools. The strength of Coriolis is that all the tools are truly integrated in memory, so they can communicate quite easily between them, and it's quite efficient. So to get back to yes, two-thirds of my time, 20 years, with uh, 2 or 3 PhDs of 3 years long, and
So,
collaboration with Marie Minerve.
yeah, that's right. I think Barry Minerve and also staff have with Coriolis collaborated, and they have in his blog he has some information about ADCs. I see John here, and he's like targeting like high speed ADC, so maybe it will be also interesting for him to dig in. My additional question for you is when you see, like Coriolis, there are obviously, parts of the design flow that we see as designers as isolated structures. So how difficult will be to I know that it is important to understand the whole Coriolis, and you are the person to know so how difficult would be to, for instance, uh, isolate the part that is like place and route and to apply it somewhere else, or you know where I'm going, because this is like so far the only tool, open source tool um, that I know that uses kind of algorithm. It's open source. It does not use AI. So maybe Align has something similar, but so obviously this is like a secret sauce that you put inside. So how do you see that? Can you tell us?
I don't really understand your question, in fact.
Okay, so my question is it possible to separate and isolate place and route algorithms that you introduced into Coriolis such that to be applied with maybe some other parts, of the script somewhere else?
Yes, I think so. The place and route is quite autonomous. You have to, the interface is not documented, but it's well defined. And yes, you can do that. It can be separated. The problem is more documentation than actual implementation.
Yeah, thank you. Sorry for not being clear earlier.
No, no.
I can see Achilles is raising his hand. Achilles, please go ahead.
Well, hello. I'm one of the
Hello.
participants of the bootcamp.
We can hear
I
that.
had, I, you can hear me?
Yeah, well, we can hear the echo, so maybe go into the separate room. Okay, thanks, Achilles.
Well, the thing is that where is the repository? It's like the some of the first questions that I have.
I think Mirjana can send you the link. It's on the GitLab of the Lip6, gitlab.lip6.fr, and under that you have Coriolis. In fact, there is a group. There is EDA tools, and there are 3 repositories. I think there is the Coriolis repository, which contains the software. You have Alliance Check Toolkit, which contains the example that I did show you, plus a lot of digital examples. And you have TASYAGL, which is a static timing analyzer, but it's another topic.
I think that in page 8 you show us like
Page 8.
The image here, like the work, right? That some person has to do to use Coriolis. So in this part, the sizing.
Sorry, which transparent? Page 8. Page 8.
Yeah. Maybe you can share Jonathan Paul so that we see like exactly what Achilles is asking. Is that possible?
Yes, I will share the transparent again.
Thanks.
Okay, so for me, page 8 is this one.
Yes, it's the sizing part. It's about the size of the components of a layout. And that part is made manual. Well, in the analog flow.
It depends, but I think it's not manual. You have algorithm to compute the right size, because the problem is that sizing is an extremely complicated matter, because every component has influence on every other. So it's very, very complex we at Lipsys, it's not my part, but we have a tool which called CIAN, which provide not a set of circuits which it can size. That is, it's not any design, but it provides a set of predefined design that it can size. According to some kind of technology, you have to have the SPICE model of the transistor for the considered technology, for the target technology, but it can be done. But in general, the sizing is a complex matter, and I think there is no tools to do that, at least not widely acknowledged.
Interesting. So, where does the designer has control in this flow? For obviously in the analog design board, but inside, like maybe in the analog place and route, the designer can do something.
What is your question? I didn't hear very well.
Like if the designer can fix a route, for example, fix a road, for instance, fix a size, the size of a component.
Not exactly, because when you perform sizing, you don't have any idea about the relative placement of your components. Sizing is just getting your component a size. You want, I don't know how many nanometers for that transistor. It doesn't tell you which relative position it will be regarding to other components. So you cannot specify a route at that stage. It would be possible if you have the slicing tree. If you have the slicing tree, it's not implemented yet, but still you can, it could be done that you can specify the exact route you want for the wire. But you need a slicing tree. You need not only the sizing, but you need the slicing tree. Without a slicing tree, or any kind of placement, for instance, you cannot define a wire.
Right. So the control is in the analog design, in the part where you define the slicing tree.
Yes.
Perfect. And the other thing is when we has this layout GDS component, right, after the place on road, it has an internal representation or directly compiles into the GDS?
I know it's direct GDS. It's
directly
GDS.
GDS, right.
I have an internal representation, of course, but it's not saved.
No, okay, but like a data structure, a class, something like that, that then you do compile and generate the thing.
No, it's the straight GDS.
Perfect. And I have a last question. Is there any company outside the one in which you are working that are using this tool? That is using this?
No, not that I am aware of. I am working at a university, not a company, but no company, because you must understand that this is, I would say, an advanced proof of concept. There are still problems, still bugs to be solved. The overall things work. It has proved that it can work, but still it's not finished due to the lack of human resources. We did not have time to finish it. We are advancing slowly, but stubbornly.
Okay.
Wait,
Thanks a lot, Jean-Paul.
I can see Jorge. Jorge, can you please ask your question if you around?
Oh, hello. Thanks a lot, Jean-Paul, for your presentation. Actually, yeah, my question is very similar to what Miriana was asking. Yeah, from what I understood, some of the functions are complementary to other to other tools that are being studied during the bootcamp. For example, the Lego 2 layouter. If I understand well, the Lego 2 layouter is more focused on particular layout of let's say cells or smaller blocks, or at least for the moment, that's what I've seen. While the the Coriolis tool is really going up into the more place and route activity, taking these cells, which in digital are standard cells. Here we would have the analog standard cells, let's say, coming from Lego 2, and then Coriolis could be able to place and route these cells. Please let me know if I'm understanding wrong, or how do you see this topic?
In fact, I don't know the Lego tool due to the lack of time and some problem that I did have recently. I didn't have time to look into it. Nevertheless, what I can say is that it's possible to import extra cells inside Coriolis. I mean, we have our own generators for transistor, for devices, but it could be it is possible. I mean, I could implement that functionality. It's not very complex to import GDS from extra cells, and then you have extra tools that generate the devices, and then they are placed en route by Coriolis. You will the thing that you will lose is that you will not able to deform the slicing tree as you wish. Because if you import a cell, it will have a fixed aspect ratio, so no way to deform it. So it will restrict.
Yeah, to restrict the, for example, splitting devices into several fingers and this kind of thing. I see.
Yes, you make that choice inside Lego, not inside Coriolis.
Okay, interesting. Thanks a lot.
Okay. Anybody else with additional questions? Okay.
Hello. So Coriolis, if I understood that correctly, Coriolis is there for the placement and routing of already created devices to place. So for the figures that you showed, right? There's D1, D2, D3, D4. So those are the devices that you place, and then you route them with the Coriolis. So is it? Am I correct in thinking that the difference between Coriolis and say Lego 2 or Bag, which is like older, maybe, is that Lego 2 and Bag are generators for those devices, and then maybe if you're thinking of like how we're going to marry these, maybe those those generators will be the ones to make the devices like the D1, D2, D3, and then Coriolis will be the one to place and route. Also, another question is that how were those devices made? Were they manually made and then you route them with Coriolis?
No. In fact, Coriolis provide both. That is, it provide place and route, but it also provide the generator for the devices. It's completely integrated. As I said previously, you can also, it is not implemented yet, but there is no question that we can import device generated by the outside. But in that case, it's less integrated. The whole point of one strength of Coriolis is also to be able to control the devices that he wants to generate. I am generating the transistors. Is that the answer to your question?
Yes. That was what I was asking. Yes, thank you.
It's fully self-contained. You have the transistor generator. You have the devices are generated by Coriolis, not by handwritten script. It's completely automated Python script. It's the stack script that I show in my presentation. The stack scripts is in charge of generating any kind of devices, of transistor devices.
How wait, did I mute tone? No, I didn't. How is it in terms of say switching PDKs? I'm sorry if I just missed that. So if you wanted to say use a new PDK with Coriolis, how would you go about trying to do that integration?
Alors, for that, we have, of course, we need information about the PDK. You cannot draw the devices without knowing the rules of the PDK. So in that case, we have a file which is called a DTR, Design Technological Rules, which basically is a transcript of all the rules of the PDK. And using that file, the stack generator draw devices that should be DRC correct. In fact, maybe I could share my screen once more. Do I have the DTR under hand? No, not here. Okay, we'll kill this one. Puff, no more this one. And do I have the DTR? Yes. I hope you see it. So you have the physical grid. Here is the DTR for the, as I already told, SCMOS CIAN Deep 09 is the 180 nanometer technology from MOSAIC. And what you have is, for example, here you have the N well, the size of the N well, the minimum width of the N well, the minimum spacing, min area, and so on. You have all the description of the rules. In fact, you take the rules that I supplied to you by the Foundry, and you write them down in that Python file, and then the generator can work. So this is how we perform the technological portability. Alors, this is not perfect because maybe sometimes there are new rules that pop up. That is, stack can only take into account rules that I know and understand. But sometimes with newer technology or corner case technology, you may have some rules that pop up, and then you may have to edit the stack script to take into account those new rules. But it shouldn't happen too often.
Can I ask you, Jean-Paul, if I remember correctly, staff, there is this collaboration between Lip6, yeah, and staff. So he is actually working on this PDK master, and that is basically a part of the script that should extract directly from DDK some information that is necessary. So if I remember correctly, within this collaboration, he was able to do that and prepare this information. And I'm looking actually, and I will post it also, his latest, like, though he was not able to join boot camp, like to present, because he's like targeting beginning of October to finish with his work. I think it is like very interesting to see what like collaboration, when you kind of complement each other, what can generate. So yeah, I think that the pain point for all these generated methodologies is basically a technology information, how to extract it fast and basically be really technology portable. Yeah, that was not a question.
Yes.
I'm sorry.
No, but we are very aware of that point, and this is our goal. We are already collaborating very closely with staff, even if it takes a different approach to make analog design. Nevertheless, that's the idea is that I want Coriolis to be inclusive. If people want to do things differently, I won't make any limitation or problem, so they can use Coriolis, even if they are in competition with my own part, at least, of my own software. It's the richness of the ecosystem.
Yeah, excellent. I think we are working in the same direction, Jean-Paul, because we would like to kind of enable the same thing. But okay, let's see how we can work better together. Yeah. Any other questions? I'm sorry. From the
Sorry.
audience.
I have more questions. So for stuff like bag two and Lego two, we have restrictions with how exactly we can size the transistors, right? So there are restrictions with, say, the relative sizes of transistors. You can only change the minimum size of, say, a grid in Lego two, and also in bag there are restrictions with so transistors in say a specific row. So are there restrictions to the freedom of sizing in these Coriolis generators in the same way, or are you completely free to size your devices?
Um, Basically, there is always restriction because the technology doesn't allow anything. So you will cope with restriction. For Coriolis, there is not too much restriction, I would say. You can choose any width or length for the transistors, because I told about the transistor because this is the generator I did write personally. So you can choose any width or length, assuming that you do not violate any rules from the design kit, of course. And you have also another problem, which is some kind of discretization and digitalization. When you start to cut your transistors into finger, if you fold your transistor 2 times or 4 times, then you will not be able to reach exactly the size you want due to the design rules and the drawing rules. You will not be able to draw exactly the length you want. But aside from those limitations which are linked to the technology, there is no limitation for the transistors in Coriolis. And the same goes for the capacitor and resistors. You will only be limited by the rules, the design rules. You cannot do everything you want at some point.
I see. Okay. So last question from me, and it's more of a perspective kind of thing. You mentioned that like you at the academia use it, but it hasn't really picked up too much for the like industry for industry using it like right now. And why do you think that is at the moment?
That's very complex question because there are many factors that come into play. For example, the industry is reluctant to invest on a tool which is not backed up by a commercial entity. They said, okay, it's university, so we don't know if the researcher moves on, and we got stuck with an unmaintained tool, which regarding Coriolis, it's not true because that's 20 years that we are maintaining it. But still, this is difficult to defend. You have another problem, is that I think the problem is more general for analog tools. I don't know, but maybe I am not the best informed in that topic, but I am not aware of any tool, academic or otherwise, that has taken root inside the industry. There are trials, there are essays, but basically when you go into an analog design department, they do everything by hand. They may have their own scripts, they have their own tools, which are little tools, little helpers, but there is not a real tool, like for example, in the digital realm, you have Encounter for the place and route and Synopsys for the synthesis. So those are well-established tools, and people are using it, really using it. But analog design tool, I don't know of them. They are not used, and there is a reluctance for the industry, and it's not proven yet. So it's difficult. I don't know if I have been very clear.
Yes, I understand. So you're saying it's more of a they're concerned about the guarantee of support coming from just the 4 or 5 developers.
Yes, they don't want to invest into something that could collapse.
I see. Okay. Thank you for the presentation. That was all of my questions.
I had a little practical question. The thing is that I've seen the licenses of the software, and it says that it is GPL, right?
Yes, mostly.
Can we use code from this from the repository in tools that are going to be used in a company or something like must be kept secret or something like that? I don't know.
Is GP there are different parts in Coriolis. You have the database at its core, which is Hurricane and which is LGPL. So for this one, there is absolutely almost no constraint of using it inside a company. For the rest of the tools, which are GPL, it's the GPL. So you have the constraint of the GPL, that is, you have to publish back the part you modify, if I remember well, the GPL requirement.
So if can you close the door? So if in our project, right, that it's open source, we used your software, we shouldn't have any problems, right?
If you are open source, no, there shouldn't be.
No incompatibilities with Meet or that kind of license, Apache, for instance?
No, I don't think so. I am not a lawyer, but I don't think so. As long as you can combine different kind of licenses, as long as they are open sources licenses, there shouldn't be any problem.
Right. Thanks a lot for your presentation, John Paul.
Thank you.
Okay, any more questions? Well, Jean-Paul, it seems that this is it. Thank you so much for your time.
Wait.
Oh,
Sorry.
okay, not yet.
One question regarding the routing. How can we control the width of the wire according to the required current?
There is a parameter. It's not working well now because of the vias. There is one little bug remaining in the vias, but the user can specify the wire width it wants.
Okay,
it's up to you.
Okay. Can we already mapping the electromigration equations from the technology to the Python scripting? So we just put the input as a current and the tool can get the width automatically or directly before the routing?
No, you have to compute it yourself, but it's Python script. If you want to write a Python script that make that computation, that's completely doable. It's just a little script. You input your currents, compute the constraint, and give back a wire width. And I see no problem in doing that, in automating that.
Okay, anybody else? So I will stop